7 days ago, on April 20th, 2026, a magnitude 7.4 earthquake struck offshore Iwate Prefecture in the Sanriku region of northeastern Japan. The ground shook. Tsunami warnings were issued along the Pacific coastline. Millions of people reached for their phones, checked evacuation routes, and waited. The quake was powerful enough to be felt across a wide swath of the country, powerful enough to trigger the early warning system that interrupts every broadcast in Japan and sends alerts to every phone. Simultaneously, powerful enough to remind every seismologist monitoring the country's dense network of sensors exactly what they have been warning about for decades. But the Sanriku quake was not the earthquake Japan's scientists fear most. It was not the one that has haunted every disaster preparedness meeting, every government briefing, every emergency simulation for the past 80 years. That earthquake has not happened yet. And the reason scientists are more alarmed now than at any point in living memory is not that the big one has arrived. It is that every signal they know how to read is telling them the conditions for it have never been more mature. The clock that has been ticking since 1946 has been running for 80 years. And 80 years, along this particular fault, is a very long time to wait. The fault in question is the Nankai Trough, a submarine trench running approximately 800 kilometers along Japan's Pacific coastline, from Suruga Bay, south of Mount Fuji in the northeast, past the Kii Peninsula and the coast of Shikoku, all the way to the Huguenota Sea, southeast of Kyushu in the southwest. It marks the boundary where the Philippine Sea Plate is being pushed beneath the Eurasian Plate at a rate of several centimeters per year. That sounds slow. In geological terms, it is not. Every year that passes, the Philippine Sea Plate grinds a few more centimeters under the Eurasian Plate. Every year, the stress accumulated at the locked contact zone between those two plates, the zone where the plates are stuck together rather than sliding freely, increases. Geologists call this stress accumulation. The plates cannot slide smoothly. They lock. They bend. The overriding plate warps upward as the subducting plate drags it down. And then, when the stress exceeds the frictional strength holding the plates together, the locked zone ruptures. In seconds, decades of accumulated strain is released as a magnitude 8 or 9 earthquake. The seafloor lurches upward by meters. The water column above it is thrown violently upward, and a tsunami begins. This has happened before. The geological and historical record of the Nankai Trough is one of the most extensively studied seismic records in the world, stretching back over 1,300 years to the Hakuho earthquake of 684 CE. In that entire period, major Nankai megaquakes have occurred at intervals of roughly 90 to 150 years. The pattern is not perfectly regular. The intervals have varied, but it is consistent enough that Japanese scientists have long treated the next rupture not as a question of if, but of when. The most recent pair of major Nankai ruptures occurred in 1944 and 1946, the Tonkai earthquake of magnitude 7.9 and the Nankai earthquake of magnitude 8.0, striking approximately 2 years apart. Those events killed thousands of people and generated tsunamis that reached heights of several meters along the Pacific coast. They occurred at the end of World War II, when Japan's ability to respond to disaster was already stretched to its limits. And since 1946, the Nankai Trough has been silent. 80 years of silence, 80 years of stress accumulation, 80 years of the Philippine Sea Plate grinding beneath Japan, adding to a load that the fault will eventually, inevitably, release. Japanese seismologists have watched that accumulating stress with increasing urgency. On August 8, 2024, that urgency reached a new level. A magnitude 7.1 earthquake struck in the Huguenota Sea off the coast of Miyazaki Prefecture on Kyushu, exactly on the southwestern edge of the Nankai Trough source zone. The Japan Meteorological Agency held an emergency meeting that same evening and issued something it had never issued before in the history of the current warning system, which was established in 2019, a formal Mega-Quake advisory for the Nankai Trough. Not a prediction, not a confirmed warning of an imminent event. An advisory, a formal statement that the probability of a major Nankai earthquake occurring within the days and weeks following the August 7.1 event was meaningfully elevated above the already high baseline. The advisory was eventually lifted, and no Mega-Quake followed immediately. But the August 2024 event marked a turning point, in how Japan's government and scientific community communicate about this threat. For the first time, the word Mega-Quake advisory appeared in official government communications to the public, and nobody who works in Japanese seismology treated its eventual lifting as a signal that the danger had passed. In January 2025, the government's Earthquake Research Committee published its annual assessment of long-term earthquake probabilities across Japan. The number for the Nankai Trough had changed. The previous estimate, which had stood at approximately 80% probability of a magnitude 8 to 9 earthquake within the next 30 years, was revised upward and widened. The new estimate placed the probability at 60 to 94.5% or higher, with the committee noting that the revision reflected new analysis of historical ground uplift data at Morodo Port in Kochi Prefecture, and the recognition that plate strain accumulation along the trough is not constant but variable. The committee chairman, Honorary Professor Naoshi Hirata of the University of Tokyo, stated in public remarks following the release that an actual earthquake is an unpredictable natural phenomenon, and that the committee cannot clearly say when it will happen. It may be more than 30 years away, but may come within a year. The phrase that emerged from every subsequent media report and government briefing was the same. The situation remains one where it could occur at any time. The numbers attached to a worst-case Nankai Mega-Quake have grown steadily more alarming with each successive government assessment. In March 2026, the Japanese government released its most recent worst-case scenario projection. If a magnitude 9 earthquake ruptures the full length of the Nankai Trough simultaneously, the scenario that seismologists call a full rupture event, where all segments of the trough break together rather than in succession, the projected death toll is up to 298,000 people. That figure represents fatalities from the earthquake shaking itself, from the tsunamis that would follow within minutes along hundreds of kilometers of Pacific coastline, and from fires, building collapses, and the failure of infrastructure in the immediate aftermath. The economic damage is projected at 292 trillion yen, approximately 1.9 trillion US dollars at current exchange rates, making it the most expensive natural disaster in human history by a margin that no other projected event comes close to. The tsunami waves in the worst-case scenario reach heights of more than 10 meters at multiple points along the coast. In some low-lying coastal communities in Kochi, Mie, and Shizuoka prefectures, where the topography offers little natural protection, tsunami arrival times are estimated at under 5 minutes from the moment of rupture. 5 minutes from a magnitude 9 earthquake to a 10-meter wall of water is not enough time to reach high ground on foot from a standing start unless the infrastructure for doing so has been built and rehearsed in advance. That infrastructure has been under construction for years, and it represents one of the most extensive disaster preparedness investments any government has ever made. Japan has built more than 400 tsunami evacuation towers along the Pacific coastline, concrete structures rising 15 to 20 meters above sea level, accessible by staircase, designed to hold entire communities above the tsunami inundation zone. Seawalls have been constructed or reinforced along hundreds of kilometers of coast, some reaching heights of 15 meters. The town of Kuroshio in Kochi Prefecture, which sits in one of the most exposed positions on the entire Pacific coast and faces projected tsunami, heights of 34 meters in the worst-case scenario, the highest projection for any coastal location in Japan, has built evacuation towers and conducted evacuation drills so frequently that a significant portion OF the town's population can reach high ground within the critical first few minutes of a warning. The National Earthquake Early Warning System, operational since 2007, detects the initial P waves of an earthquake, the faster, less destructive seismic waves that arrive ahead of the slower, violent S waves and surface waves, and broadcasts alerts via television, radio, mobile phone networks, and public address systems within seconds, providing between a few seconds and approximately a minute of warning before strong shaking arrives, depending on distance from the epicenter. What has changed in the past 2 years is the integration of these warning systems with real-time monitoring data in ways that were not previously possible. Japan operates one of the densest seismic monitoring networks on Earth, more than 4,000 sensors distributed across the archipelago, feeding data continuously to the Japan Meteorological Agency and to the National Research Institute for Earth Science and Disaster Resilience. Offshore, a cable network of seafloor sensors called DONET monitors pressure changes, temperature, and seismic activity directly at the Nankai Trough's source zone, the first ocean floor monitoring system of its kind deployed at a major subduction zone. DONET data goes directly into the JMA's analysis system and can detect the initial rupture of a seafloor earthquake within seconds of it beginning. The practical implication is that warnings can be issued to coastal communities before the tsunami has even reached the shore in many locations, a capability that did not exist during the 2011 Tohoku disaster, when the tsunami arrived in some locations faster than warning systems could respond. The 2011 Tohoku earthquake and tsunami is the event that permanently restructured how Japan thinks about this risk. On March 11th, 2011, a magnitude 9.0 earthquake, the most powerful ever recorded in Japan, ruptured the Japan Trench off the Pacific coast of northeastern Honshu. The seawall that was supposed to protect the town of Taro in Iwate Prefecture, the largest seawall in Japan at the time, was overtopped, the Fukushima Daiichi. Nuclear power plant lost power to its cooling systems and experienced 3 reactor meltdowns. Nearly 20,000 people died, the majority from the tsunami, not the earthquake itself, despite Japan having the most extensive earthquake early warning system in the world. The lesson that Tohoku forced onto Japanese disaster science was the same lesson that has shaped the Nankai preparedness effort ever since. The question is not whether the engineering and warning systems work. It is whether the people who need to use them actually use them when the moment arrives, whether drivers stop their cars and run for high ground rather than attempting to evacuate by road, which blocked every coastal route within minutes of the 2011 tsunami. Whether residents in inundated areas who received warnings chose to act on them rather than wait to see how serious the shaking was before deciding to move. The slow creep that scientists have been measuring at the Nankai Trough in recent years adds a specific technical dimension to this picture that goes beyond the general probability statistics. Several research teams studying GPS data from coastal monitoring stations in the Kii Peninsula and Shikoku have documented what seismologists call slow slip events, episodes where sections of the locked fault interface slip slowly, releasing small amounts of strain over days or weeks rather than seconds without generating a felt earthquake. Slow slip events are significant because they indicate that the fault is not uniformly locked. Parts of it are moving. The question that nobody can currently answer with certainty is whether slow slip events relieve stress in a way that reduces the risk of a catastrophic rupture, or whether they represent the fault gradually preparing for one. In some subduction zones around the world, slow slip events have been observed accelerating in frequency and magnitude in the years and decades before major earthquakes. Whether the Nankai Trough is following a similar pattern is one of the most actively researched questions in Japanese seismology. The April 20th, 2026 magnitude 7.4 earthquake off Iwate did not occur on the Nankai Trough. It struck on the Japan Trench, the subduction zone responsible for the 2011 Tohoku disaster, hundreds of kilometers to the northeast of the Nankai source zone. But it arrived as a reminder, in the way that every significant Japanese earthquake now arrives as a reminder, that the country lives permanently inside a seismic environment that is unlike anywhere else on Earth. Japan accounts for roughly 20% of all magnitude 6 and larger earthquakes recorded worldwide. It sits at the convergence of 4 tectonic plates, the Pacific Plate, the Philippine Sea Plate, the Eurasian Plate, and the Okhotsk Plate, in a configuration that makes major earthquakes not an occasional catastrophe, but a permanent condition of existence. The 1 in $500 detectable earthquakes Japan records every year, approximately 1 every 6 hours, are not anomalies. They are the baseline. What the Japanese scientists who have spent decades studying the Nankai Trough are saying now, in the language of probability, ranges and official advisory systems, and revised worst-case projections, is that the interval since 1946 is now longer than any safe historical precedent. The last pair of Nankai Mega-Quakes in 1944 and 1946 struck after a gap of approximately 90 years from the previous pair. The current gap is 80 years and counting. The stress meter is full in every model that has been built to estimate it. The warning infrastructure is as prepared as human engineering can make it. The evacuation towers are built, the drills are running, the seafloor sensors are transmitting, and the early warning algorithms are live. Everything that science and engineering can do to prepare for a Nankai Mega-Quake has been done, or is being done. What cannot be done is predict the day. What cannot be done is release the stress before it releases itself. And what the scientists who know this fault best are saying consistently and with increasing urgency in every official publication and every public statement over the past 2 years is that the moment they have spent decades fearing is not a distant abstraction anymore. It is the present. It is now. And the only question that remains is exactly when.